Hello, welcome. Good afternoon. Thank you for being with us today. We're broadcasting live from Park City, Utah. And where are you, Adele?
Vancouver Island,
Okay,
Canada.
Canada. And Mark, I don't know where you are. Are you in California?
Yeah, just a little outside of San Francisco, Marin County, Mill Valley.
Yeah. And Noel, you're
And
in.
I'm outside of Toronto, Canada as well.
Oh, awesome. So thanks everybody for being here. Big, big hug and thank you to my dear friend Adil for introducing Mark and his firm to Family Office Insights and me. We actually met, I don't know, it had to be 6 years ago, something like that, right? Maybe four, maybe something like that, five. So I'm super glad to have gotten updated. Happy to have you guys. And you're doing some really fantastic things. And I'm anxious for the group to hear what you're up to and the progress that you've made. The science is way over my head, but I think I've connected the dots a little bit. So I'm super excited about hearing it. As you know, we're on Zoom. We're going to be recording this, and depending on where and if we share it, we'll let you know. And for the record, if there's anybody that you think of in your network, your community that would benefit from hearing what you hear today, you can share the recording, or you're all going to be connected directly with Mark and company post webinar, and so you're most welcome to connect with them directly. As we go through the presentation today, please feel free to post your questions at the Q&A in the chat box. We can't take audible questions, but you can, and you're most welcome to, and I would recommend that you post them as they come to mind, as we have a bunch of people coming on today, and we'll get to as many as possible. So again, thank you, Adil, for arranging this, and Mark's so welcome to be here. So with that, we're going to do a little bit of overview with little backgrounds, and then we'll get into the meat of the matter. We're going to have a bit of a presentation today. And so again, feel free to ask questions as they come to mind. And Mark, please take it away. Welcome.
Okay. Well, thank you, Arthur, as I'm adjusting my camera in real time.
You look good.
Yeah, I just got a little chat there. It says, adjust your camera. So I'm doing it. Yeah. So, well, yeah, the technology is pretty easy to explain. We do this stuff over by this place with these people. So that's pretty much it. Well, yeah, thanks for having us today.
Yeah.
So I've got Noel and Adele on the call, Lauren, support team, COO, marketing. And basically, what we are is our entity, Singularity Group, has been an incubator and an accelerator of some pretty extraordinary technologies based on this principle of what we call resonance physics. And the reason I shared that in the beginning is because some of the things that we talk about of what the technologies actually do, people at the beginning have a little hard time believing that these things can actually do what we say. So it's important to just provide a little bit of a foundation that what we're doing is not so much just taking some idea and trying to make it better, but it's a foundation of a really important new understanding of how we look at energy and material sciences. And so today what we're talking about is sort of our crown jewel company called Centuri. And what Centuri is a company that has developed multiple applications of a composite material. And we're really focused on 4 applications of the composite material. So and I can probably, maybe we'll just take maybe 1 or 2 more minutes, let a couple of people come on, and then we'll dive into the meat of it. But just to give a little background, which is not so much on the presentation, this is something that we've been developing for 19 years. And the good thing is in some ways we're a startup from going to manufacturing, but we're far from that in that we've used many real world applications of the technologies, and you'll see in a moment. And now it's just this this very interesting inflection moment whereby we're now saying, okay, now we know how it works, we know how to implement it, we've got all the devices and technologies built that we want to have right now for the application. And so we're just transitioning from sort of an R&D application entity into a manufacturing go-to-market entity with all of the interest that we have. So here we're talking about raising capital to actually manufacture and go to market. So that's the foundation today.
Mark,
And so,
if you're going to get into it later, but I'm under the impression, and I'm often wrong, so let's put that out there, that this resonance physics, did I say it right?
Yes.
Is something that isn't sort of the established physics that someone could reference and understand what it is. This is something relatively innovative.
Yeah, so two answers to that. If we were to access the majority of content that we would say, if we're going to look at the current known physics today, the answer would be yes. Over the last 18 years, we've been publishing a pretty significant body of papers to quantify this understanding of resonance. And basically, what we're talking about resonance, meaning all we're doing is saying, let's look at how nature functions, and then let's create technologies and systems to emulate nature. Because what we would say today is that everything that humanity is doing is dissonant to how nature functions. You know, we blow up hydrocarbons, we split atoms, we use chemicals on humans and plants. And, you know, nature doesn't do any of that. And just to give you probably one of the most fundamental little inquiries into this. So if I reference that physics that you were talking about, the known physics that constitutes, 99% of the science out there, if I ask any physicist, engineer, scientist on planet Earth that's well versed in that, the standard, they call it the standard model, like a couple really basic questions. And one of my favorite is 750, approximately 750 trillion magnets are out in the world today doing a lot of work. And with the electrification of the world, a number of magnets they're used in electric motors is increasing significantly. But if I ask any physicist, scientist, engineer on planet Earth, and there may be some on this presentation today, how does a magnet produce more work than energy it consumes? Like if I put it on my refrigerator with a little piece of 8x10 paper, it'll hold up that piece of paper for 10 years. If my arm had to do that, after 10 years, that'd be a lot of energy expended. And the first response always, well, it's the electromagnetic force. Okay, where does that come from? Right? And there's no explanation. Actually, there's a couple of YouTube videos like from Richard Feynman, one of the greatest physicists of today, or in our modern time. And somebody asked him a question, how does a magnet work? And then you see one of the greatest minds ever start to melt down, get pissed, and walk off the stage, right? Yeah, so it's pretty interesting. But our physics clearly articulates in pure mechanical math that the magnet comes from this electromagnetic field that we live in, that the space is filled in, and we're just tapping into that field. And then that exact same principle can be extrapolated across everything that we're doing. And that understanding explains how we've made this really extraordinary jump in a composite material, how our wind turbine seems to defy standard laws of physics. But so that's just one of many examples of what our current physics can't explain really anything. Where the energy of the nucleus of the atom that's spinning at near the speed of light comes from. Ours quantitatively explains all of that. So, but we won't go into that today. We'll just talk about materials.
Yeah, that's super helpful as a little sort of starting point. Thanks for doing it. Yeah,
absolutely. Okay, so maybe we'll jump into the meat, huh?
Sure.
Or for the vegetarians, the tofu.
Yeah.
Okay. So the name of the company is Centuri, and we'll just go past that. So basically, our mantra is that we're bringing to life a revolutionary composite material that we think will change many industries because of what can be done from it. So the material, just a couple of bullet points that are important. it's 6% the weight of steel and 10 times the strength. And if there's anybody on the call or the presentation that has an understanding of composite materials, very often they're difficult to work with. Ours is all done, as you can see on the table there. No autoclave, ambient pressure, ambient temperature. So it's very, very easy to produce at scale. For instance, in 1 million square feet, we would just have very long production tables. We've had it third-party fire rated to 1350 C, so 3000 F. We can go higher. That's just what we have it rated as. And we may have some images on here. I can't remember exactly, but it has very interesting properties that there's no heat transfer. So even if you're holding the composite, and here it's 1350 C, that your hand 2 inches away would have no heat. It won't rust, corrode, of course. Or when we say affected by liquids, the important part of that is that the size of the cross-linking and the molecular structure is really the same as steel or stainless steel. So we can build, for instance, tanks from it that we could have fuel in it one day, rinse it out, and then put milk or water in it the next day. So it's the only composite material that has that dense of cross-linking. We believe it's the greenest material on planet Earth. It's significantly made from plant resins. And the way in which we make it, which is just forms, we can really mold it into any shape or any design. So over the last 18, 19 years, we've been developing and working with and testing the various applications that we feel would be the most significant, the most impactful, and that had the greatest financial reward. So all of those components, and we narrowed it down to really 4 things: energy, transportation, housing, and construction materials. So this is our first is our wind turbine. So first of all, that is an image of the turbine, and it's supposed to be a little video that works. It doesn't work in the PDF, so I'll switch it over to a moment just to give you a little moving visual of it. But our wind turbine, actually, why don't I do that right now?
Hey, Mark, while you're doing that, is it
Yeah.
fair to say, or is it fair to compare it to what is commonly known as a strong light material carbon fiber? Is that fair at all in terms of something to hold it a comparison against?
Well, we could compare it against carbon fiber, but it's much less expensive, significantly more versatile in how it can be used. It doesn't have the microfracturing that carbon fiber does. It has a much higher burn point. It's greener. It's stronger. So it's superior to carbon fiber in pretty much every way possible.
Fair enough.
And Noel and Adil, unfortunately, I can't access the video. Noel, can you pop out just the video real quick? Okay. Is that going to work? Oh, yeah, there you go. So, okay, yeah, so there you see it. It's actually spinning very slow because of the lag time, but it's actually spinning in real time about 45 miles per hour. And a couple of really important things, actually extraordinarily important about this. So what you see is it's a vertical axis turbine, and then there's a ring at the top, and then there's it looks like it's actually as it's buffering. There we go. It's starting to pick up speed with each buffering. So there's a ring at the top and a ring in the bottom that the core sits in, and that's all maglev. So there's nothing touching anything. There's no bearings. There's no transmission. There's no moving parts of any kind. So basically, oh, there we go. Now it's really cooking. So it's the world's first wind turbine that has no moving parts. It produces electricity at 2 miles per hour of wind. So basically a breeze, actually, and what's being held there is a wind speed meter. So it's a handheld wind speed meter. So you can see all the way down to 6, 7, 5, 4 miles per hour, 3 miles per hour. That's actually spinning at about 55 miles per hour, which that's why I talked about the beginning of understanding electromagnetics in the very beginning of this conversation is we would have to have a really good understanding of, first of all, foil design, and then electromagnetics to be able to sort of get this level of acceleration from a technology. So no friction, maintenance free for 50 years or so, 30% efficient at 2 miles per hour, 100% efficient at 11 to 12 miles per hour. Our new unit is a little bit taller and a little bit bigger base, and it's producing 1.1 megawatt. So you can now have 1.1 megawatt, and we can put it on a pole. So we could have it'd be 80 feet tall. We would have 2.2 megawatts. So one stacked on top of each other. But so in a very, very small footprint, which you'll see in a moment, we can have in a 40 foot footprint or on top of a building, 2.2 megawatts with no maintenance. We have no back EMF. We've had a much smaller unit installed near San Luis Obispo on a pier for 3 years. We've been able to validate no bird kill, because there's no back EMF. All the issues with animals and all that is resolved. So pretty much basically every challenge with wind power is resolved with our technology. So no maintenance, no transmission, no gears, no moving parts, extraordinarily light and extraordinarily efficient. So whoever is sharing that, thank you. And I'll go back to my presentation. So that's the first part of the turbine. This is all just computer graphics. That doesn't exist, but it allows you to see the density that we can provide. And the reason we provided this imaging is that one current windmill, like a 2.4 megawatt Westinghouse windmill or something like that, takes up about 2.2 acres of land. And for us, in 2.2 acres, we could have 100 megawatts. And it could be set up on anywhere. It's very light. They could be put on a barge. They can be put on rooftops. They're lighter than many large industrial heating and air conditioning systems. So this is just an artist rendering of showing what the same density is for our turbine as you would have in regular conventional windmill technology. And before I go on to the applications, did you guys have any? Did you have the video of let's say the Iceland project or anything else? Can that be done real quick?
Yes, absolutely. I can put it up.
Okay, just to show that we've been having this technology in the harshest conditions possible on planet Earth to ensure. So this is our turbine in Iceland, and it's been in up to 140 mile per hour winds and up to 40 degrees minus F, and still working perfectly. And again, that's a little lag time there, but that turbine is spinning much faster in real life. And the other one is on a garage that we had. Unfortunately, they sold the building. It was an old Genentech building in Northern California. But so you can see that we've actually had different applications of the turbine as we were developing it in practice. Thank you, Noel.
Absolutely.
So, Mark,
Please.
if you took the artist rendering on the same footprint as the single GE windmill, the traditional windmill, how does it compare in kilowatts?
Oh, yeah. Okay, so let's say a conventional windmill producing 2.4 megawatts in 2.5 acres. So in that same footprint, we can be producing 100 megawatt. But so let's say a 2.4 megawatt potential windmill is only producing 2.4 megawatts, like that would be a Westinghouse windmill at 100% efficiency, which I think is something like 25, 30 miles per hour of wind. At 15 miles per hour, I think it's 30% efficient. So even though if we had the same capacity, we're something like 300% more efficient for that same level of capacity, because we're producing
At lower wind speeds. Yeah.
we're 30% efficient at 2 miles per hour. I think the normal windmill isn't even moving until 9, 10, 11, 15 miles per hour. So the numbers are really, you get up to like 3, 4, 5, 600% increase in efficiency, and then you have no downtime for maintenance. There's no downtime for lifespan of the transmission, the gears, everything else that's required in a normal turbine, a normal windmill. So yeah, it's almost not even apples to apples, right? It's like a little sour cherry compared to nice beautiful mango.
Yeah. So I'm going to take question out of order here, just because it's germane to what you're saying. How is the energy transmitted if there are no parts touching the spinning coil?
Okay, super great question. So let's say I wish I had a little image here, but I'll just use my hands. So if the top ring is here, and let's say the coil and the turbine is here, and the turbine is spinning, okay, and you have the top ring and then the bottom ring. So in the top ring and in the bottom ring is a set of coils, okay, and then in the turbine itself, in the top and the bottom is a set of coils and magnets in both the top and the bottom of the turbine, and then the top and the bottom of the ring that the turbine sits in is a set of coils and magnets. So it's resting in there and it's just floating because of the maglev. But then as it's spinning, so just in a normal, electric motor design, really, that as you have coils passing through each other, so the coils in the turbine are passing through the magnets and the coils in the top ring and the bottom ring, that's how the electricity is being produced.
So that's super interesting.
Yes. So the coils and the magnets are embedded in a really significant proprietary design of both the coil. We make our own magnets. So our magnets, and we could get really into the physics. I think that would really kind of blow some minds. For instance, if this is a magnet, okay, and so we call the flux path. Everybody's probably seen an image of the magnet. It goes like this. That the power of the magnet. You got a little here. You got a little, and on the same with the bottom, the north and south pole. Well, most magnets today are using only this little part that's coming up. That little bit of the flux path that is coming up. All the rest of it just goes back into the electromagnetic field. It's all wasted. So really, even magnets today, Tesla motors, all of those, a very significant portion, probably 90% of the potential of that magnet is just, it's just wasted. One of our patents, if anybody was to look at it, it's really quite extraordinary. And when people look, I say, why did you patent it? Well, now we can actually direct, just like in a circuit board, you have a little channel that all the electrons flow through. Well, now what we've created is an etheric circuit board. So in the space, we can actually direct the flux path. So now we can take all of that wasted energy from a magnet and we can direct it. So that's the first part of our magnet. The second part is that we can actually pulse the north and the south of the magnet, so that as it's going through, we remove all of the back EMF. So that's why this thing can move with very, very little energy, because it doesn't go like this and then get the pushback. So that's an extrapolation on the question. But how the electricity is being produced is coils embedded in the turbine itself, in the top and the bottom. That sits inside of a top and a bottom ring that have coils and magnets in there. And then as it spins, it produces electricity.
Super cool.
Yeah.
Thanks, Tim. Good to see you here. The guy that asked the question, I know.
Okay.
Okay. Carry on. Fascinating.
Okay. My wayward son. Okay.
Yes.
It's funny, I use cultural references, and some of the younger people of my team always like, what are you talking
Yeah,
about?
what are you talking about?
Yeah, I feel old. Okay. Okay, so some other applications that we've used the composite for. One that we really like is shipping. So we've built the world's only Coast Guard approved all composite commercial vessel. This is an 82-foot catamaran. And you can see on the bottom right-hand corner there, the whole ship is being held up by one little crane because of how extraordinarily light the material is. You can even see when it's on plane, the whole front half of the vessel, is out of the water. We've also built 2 vessels for the Department of Defense, stealthy vessels. We can't show those, but we chose the ocean because it's the most challenging, harshest environment, on the planet. And that commercial vessel has now been operating for 15 years, and there's not even a ding in it, with people being on it, pretty much every day for 15 years. So we've been able to show that it's an extraordinary material that really could revolutionize shipping because it doesn't foul. It's incredibly light. It can be molded into any shape and really create sort of new designs in shipping. And but this is one of the 2 companies that we're focused on going to market. So the first is the wind turbine, and the second is the shipping containers. So the reason we're focused on this is, so for instance, we've presented this to Maersk, and I see that actually there's a little typo here, but the fuel savings is actually, we can reduce the normal weight by about almost 6 million pounds from changing from a metal container to our composite container. And we've already built these, as you can see, and they've been tested. But one of the most important things that we've come to understand about shipping is that after about every 5th or 6th use, so right there it says 5 to 7 trips, they actually have to take the container off of a ship, and then they have to inspect it for microfractures. Then they have to repair it. And it's the single most time-consuming and expensive process of shipping containers. So every 4 to 7, we anticipate, and this is a third-party study that was done, that our container could go 500 to 1,000 uses without having to be inspected. I mean, it would pretty much be impossible that there could be microfissures. But also, compared to a metal, they can be watertight, they can be insulated, so they can ship produce, so you no longer need refrigeration. So we really think that they have an opportunity to have a significant impact in shipping. And then we've just recently engaged in a conversation with the DoD, the Department of Defense, unknowns to us, that metal shipping containers is a huge problem for them. They buy tens of thousands of them a year to ship things all over the world, and they get damaged, they're heavy, they're not secure, they can't be used in cold temperatures. And so our container solves all of that. And we just got a call this morning from a group out of just outside of Toronto, Canada, that is producing massive amounts of hydrogen, and they're trying to work on containers to ship it to Europe. And so we can provide a solution for that. So we're really focused. It's such a straightforward thing for us. It's basically some tables, cutting, and molecularly welding. So we can make these really, really, really fast. We can develop them to any size and shape that anybody wants. And we have interest right now for approximately 10,000 units a year right away, at about $12,000 to $15,000 a unit. So we're really excited about the shipping container market. So that's the second use of the technology. The third use of the composite is building, which is a really rapidly growing area, affordable and tiny homes. So a couple of the reasons that we're superior to pretty much any other material out there. One is we're basically fireproof, up to 3000 F, 3500 F. There's no VOCs. So compared to maybe any other composites or even many materials, the volatile organic compounds are a real issue. Since there's no wood, we never have any issues with mold or degradation. If you look at the bottom, that is the actual first one that we built. And the reason we show that is because we can embed the, let's say the paint color into the liquid composite as we're making it. So it really never has to be painted again. And we can make the form look like any material, just depend on the surface of the form. So we made this look like wood. And inside, the flooring, the walls is all made out of the composite material. The cabinetry was purchased, third party. And then we can build in all of the plumbing and everything all into the construction process of the home. So we've got a couple of groups that represent about 3,500 homes right now that are very interested in this, and they're just waiting to see our ability to move up to scale manufacturing.
Mark, would it be okay to take a question about
Sure.
the composite?
Yes.
Are there, all this is way over my head, you'll probably get it. So
Okay.
are there EDC plasticizers used in the plant-based resins? First question.
Okay.
And how does it compare performance-wise to the basalt-based composite and the heliocoidal parentheses matta shrimp emulating composite?
Yeah. Okay, we got a big brain here. Okay, awesome. Yeah. So, so let's say, so basalt, like for instance, there's a group out of Miami that's contracted to build a really significant, I'm not sure what you call it, but it's like a water break that goes way out, like a wall that goes out into the ocean. And so, for the scale of manufacturing and some of the things that it can do, it's a good material. I would say that in most every way, our material is superior to that. I just met with that group in Miami that's doing that. They've already got contract and they started, so it's too late for them to switch at the moment. But ours would be just as strong, would be lighter. Some of the raw materials would be easier to access, and no, there are no plasticizers.
Yeah.
So, yeah, and actually, the image that is on my screen right now can kind of have a little reference of that. If we can see that I-beam there, so you could actually see how thin the material is. That's actually an I-beam for a bridge. I see we don't have the image here for a bridge, but this was a bridge in Northern California where after many years the steel had corroded, and so they replaced it. But you can see basically how strong this material it is simply just by looking at the thickness of that for an I-beam. But yeah, so no plasticizers, and I think we would compare favorably and superiorly in every way compared to basalt.
And basalt is sort of the standard?
I wouldn't know if it's a standard. It's yeah, I don't know. I mean, there's so many
We don't have to
materials.
dwell on it. Yeah, it's an uninformed question from my perspective. Yeah, continue. It doesn't matter.
I mean, basalt's been around for thousands of years, right? I mean, in
Rome,
Rome,
Egypt, yeah,
the Roman Empire, used basalt, right?
Yeah.
Yeah, so it's not a standard at all. I mean, I would say normal concrete, and things are standards. And then the question about heliocolloidal fiber is being used, and that's what carbon fiber is really, right?
Okay.
And those are, laminates that are used for really mostly for real, from what I understand, I'm not the expert on this, but I believe it's for really like high impact designs. And I don't think we have an image here, but we have somewhere the image where 3/16 of an inch thick of our material was able to catch a 45 caliber round from 10 feet away. And the beautiful thing about that is you can see that it makes just a little bit of an imprint in it, just like a little dent in space-time. And so then what it's able to do, it actually disperses the energy and also stops the impact. So, and any comparison to that for impact resistance, it would be equal to or superior than anything that we've ever seen. And we've tested that. Very significant part of our team has very, very in-depth military and DoD background. So, but we're never going, or I should say, hope to never use our technology for offensive purposes. But yeah, so for that very specific question, for impact resistance, we believe it's equal to or superior than anything.
Got it. Thanks.
Okay, if that's what the question was centered about.
Yeah, there's a follow-up. Do you want to take it or you want to keep on moving?
It's up to you.
The follow-up is thanks for explaining that, but it says the heliocoidal, that sounds really like post-coital remorse, referring not to carbon fiber, but to the pattern of layup that optimizes the impact resistance. So
Okay.
I think
I think I just described that then. Yep.
Yeah.
Okay. Okay. So we'll go back. Okay. So this is a combination of artist renderings and things that we've actually built from the composite. So the I-beam is what we've actually built. Let me see the next slide. Oh, okay. As many people are aware, a couple of years ago, Australia experienced pretty catastrophic fires that burned down millions and millions of acres. So we formed a joint venture with a group out of Australia, and we're now replacing all of that fencing and all of the ranching applications with our composite material. So this is actually our composite, and some great advantages, of course, is that it won't burn, but there's no UV degradation because, as I shared earlier, that molecular bonding density results in 0 UV degradation, and it's much easier to work with, than steel or anything. Of course, more cost effective. So we're really excited about this. So it's being we're actually having to build more manufacturing because it's growing very, very, very fast. And the farmers, the ranchers, everybody just wants to use our composite. So this is really just over about the last year or so. So those are the 4 applications that we're really focused on. Our revolutionary wind turbine, the containers, housing, and using it as building materials. And in Australia, the group there now has come with a very large, it's like a Home Depot there. They now want us to actually provide 2x4s, 4x4s, 4x6s to start replacing, which this is going to be a monster, to start replacing wood and steel, studs that they actually sell in the store because it's superior to wood and steel in every way. And
it can be fastened with screws and nails and all that business.
All of that, yeah. And this, we can provide later, but we pretty much have a very good understanding right now of what our potential of going to market is. It's pretty significant. We have about $10 billion of interest, or here even 16 billion. Just a couple happened last week or so. In the wind turbines, very significant. interest in the shipping containers. So, we're a little bit of a fascinating hybrid where we are just going to market now, but we have almost 2 decades of research, development, real world application showing that it works. And now we're funding to scale to actually start providing the manufacturing.
So it seems pretty obvious that the advantages are there for the composite. What's the delta on the cost, if any?
It's equal to or lesser than any known building material. Wood, fiberglass, 30% less expensive than fiberglass, 20% less expensive than wood. It's cheaper than steel. So it's less expensive. We can manufacture at scale. It needs no special materials. They're readily available. It performs superior in every single way. Fire resistance, VOCs, strength, flexibility.
No toxins, none of that, right?
Nope. So yeah, we really we feel it has pretty much unlimited potential because of everything that it can be built from. And then coupling that with the development of our physics, so in electromagnetism and some other things, we can then take the composite, which we've done, and even some of our manufacturing principles have been able to be facilitated because of the breakthroughs in our physics. So now, like in the wind turbine and our manufacturing overall, and even so like in the containers and other things, we can make it so the shipping that nothing sticks to it, there's no fouling. But so it's a really interesting hybrid of very advanced science in electromagnetism, and then very advanced science in material sciences to create what we've created.
So Mark, just from a very pedestrian way, when you're building a container, is it 4 or 5 or 6 panels screwed together, or is it molded?
No, yeah, here's how it works. So let's say 100,000 square foot, but we'll get to 1 million square feet pretty quick. But let's just say in our 1 million square feet, which we have right now demand for probably about 3 million square feet, but in 1 million square feet, we would have tables about 100 feet long. So we would have a mold that's 100 foot long, and we would just lay out that whole mold, so whatever the width of the container would be. And so let's say it's 8 foot, and then that 100-foot mold, we would cut them in 20 foot, or if it was a 40-foot 120 foot, so we would just cut sections, and then we just put them in a exoskeleton. Okay, we just slide them in, and then we just have a device that goes with the composite and it molecularly bonds the panels to each other. So there's no screws, there's no anything. And to give an example of how that works is that one of our other companies I started some time ago, and it's now doing very well in the market, it's a new type of refrigerant for heating and air conditioning. They're like, okay, they have to ship it in round containers, and round containers don't stack well. So they said, could you make a hexagonal container under pressure, like an oxygen tank? Well, because there's no seams, even though it has sides, because when it's molecularly bonded, there are no weak points. We actually were able to make a hexagonal pressure container because every centimeter of it has the exact same strength. So there's no screws, there's no seams. The whole thing is molecularly bonded.
Is it a cylinder inside the hexagon?
Oh no, it's hexagonal inside.
Yeah. Super interesting.
Yeah. So that's, again, it starts to really change how we look at, you can't do that with carbon. You can't do that with any other material.
Yeah.
Right. You have to, you have to find ways to adhere it to things. It's all, and we can cure it at, any time we want. Like we could cure the rate that we're going to bond the pieces together, like in 2 hours or 2 days. So, the assembly of them is dictated on that. And then it's just like looks like a big, like robotic caulking arm, or just, you put the bead of the material where the seam would be, and then it just sort of welds it all together. And then every centimeter of it, the panel where it was welded, all has the exact same tensile strength. So no weak points of any kind.
So does printing make any sense with this?
No, it's no,
not necessary, right?
No, it would be absolutely unnecessary to be extraordinarily more cost prohibitive.
Yeah.
Scaling, like, we could have 1 million square feet of production at such a low cost. I mean, we're basically talking, vacuum. It's like when for some people, if you have the little thing on your countertop where you've got leftovers and you put the little in a plastic baggie and then you put it in the machine and it vacuums and sucks all the air out. That's pretty much our process on steroids.
Yeah.
Right.
I like the simplicity.
Yeah. So the scalability is this, we have 1 million square feet. It's just tables, and then laser cutters and a couple other things. But yeah, no, we would never want to go to 3D printing and be much slower, much more cost intensive.
Unnecessarily fancy, right?
Yeah, it's a beautifully elegant, incredibly cost effective process.
Is there just one more question, and let's get into a little bit more about the ask. Is there any supply chain issues for the plant-based resin?
No, because basically the material that we take is pretty much leftover that goes to waste right now, where millions of ton go to it, and it's actually a problem. So we can, take it off their hands. There has to be a little bit of processing, soy and corn and a couple things.
Yeah.
But yeah, so a lot of it that is actually waste product is what we like.
Sounds like there might be a way to get the raw material when someone pays you and gives it to you, right?
Yeah, we haven't got that far yet, but we've talked about, when everybody sits around like, hey, what if?
Yeah.
But one of our other projects is pretty heavy in the ag space, but we haven't even introduced that conversation yet.
Yeah. So let's okay. Sorry. Are
Okay.
there any environmental concerns, for example, recyclable, biodegradable? What criticisms do you hear regarding your materials, if any?
Oh, none ever.
Yeah.
Nope. No, never heard. I would love to hear one if it's possible. Yeah, no, never to date. I'm not aware of any that's ever been contemplated.
Yeah. So let's talk a little bit about use of funds, what exactly the raise is for. And you mentioned it a couple of times, but let's talk a little bit more about it.
Yeah. So basically, our entire world now is doing two things. One is we've identified a property in Oxnard, California, where we now know the exact specifications that the market wants for the 1.1 megawatt turbine, for the 20-foot and 40-foot shipping container, and an 840 square foot home. So we are going to build what we've already built, but to the exact market specifications, those four things. So the 1.1 megawatt turbine, the 2 shipping containers, and the home. We already have all the building materials. They can come visit that now. Then that will allow us to then begin finalizing sales. So that's basically everybody wants to see. They just want to come in, make sure it has all the the appropriate certifications and all that. So we'll do all of that in the Oxnard facility. And then we've identified 2 locations, one in Las Vegas and one in Texas of about 500,000 square feet, where then we will do manufacturing. And we pretty much have it down exactly to every 100,000 square feet, what the revenue potential of that is. So the use of funds, $30 million is for initially the facility in Oxnard, California, to build out, have all of the certifications done at that location, and sort of all the prototyping, go to market units ready there. And then where things are much more business friendly and less expensive in both Nevada and Texas, we're choosing one of those two locations for manufacturing. We want to do both simultaneous. It'll take us about, we'll have the homes and the containers built in 60 to 90 days. We already have the forms, so we're pretty much ready to go. The turbine will take about 6 months, but then at the same time, we'll be building out our manufacturing facility. So then by the time we have all the certifications and the go-to-market units done in Oxnard, we'll have the manufacturing up and running, or be able to be up and running.
And once the manufacturing is able to be up and running, is the time compressed to scale being able to sell the, let's just call the wind turbines?
Right.
Is it, a month to build one? If you have a
no, so
Yeah.
for every, okay, and that, Noel, make sure I got my numbers right, hop in. So for every 100,000 square feet is 25 megawatts a month.
That's correct.
Okay. Yeah, so we can produce for every 100,000 square feet, and we're being very conservative on that because as we add every 100,000 square feet, there's not some things don't have to be replicated.
Yeah.
So for every 100,000 square feet, we can build 25 megawatts a month. And then for every 100,000 square feet, I think it's 500 or 1,000 containers a month. I can't remember. What is the number, Noel?
I think it was 1,500.
Okay. So for every 100,000 square feet, it's 1,500 containers a month.
So, I'm not sure this is the right way to look at it,
Yeah.
but let's just talk about the wind turbine for a minute. Everybody is become aware, if they weren't, or many people have become aware if they weren't, what the cost of electricity is because of all the Bitcoin mining, et cetera, et cetera, et cetera. Can you draw a comparison between what the 4 or 5 cents, 6, 7, 8 cents the electricity cost? Can you compare it to what it would cost with the turbines?
Yeah. So let's say if we're in a 50% efficient environment,
Yeah.
so we have at least 7 to 8 miles per hour of wind, which that's most places. So if we take the CapEx cost over 3 years, so the first 3 years the cost is 0.01 cents per kW, and then after that it goes down to much less than that because you have the CapEx cost is pretty much gone. So yeah, it's minimal again because like a regular windmill, you've got $25,000 to $45,000 a year per megawatt in maintenance. With us, you have zero. The CapEx cost is 1/3 to 1/5 the price of current wind technology, 1/3 the cost of solar. And then if you actually calculate in the production, I forgot what, there's 3 letters for that, like meaning what your potential capacity is and then what your actual production is. I forgot what the acronym for that is, but it's so superior, to solar, to windmills, to pretty much anything. Maybe like we know a group that has a facility up in Elko, Nevada, where they're taking geothermal and they're converting the ammonias into hydrogen. And so they've got a pretty cool technology doing that with plasma. And we're talking with them about making it a little better, but that's very efficient. As for if you're able to use hydrogen. But besides that, yeah, so compared to, let's say, 4 cents, we're 1/10 of the cost of 4 cents. 0.001 cent.
Yeah.
Yeah,
Um,
1/10 of a cent.
so back to the time frame to deliver containers. We have another question about that. If you got, your raise in the form of whatever, I imagine you're doing equity, but you could probably, if someone was willing to give you debt, you'd probably take it, right?
Yep.
Yeah.
Here's my routing number.
I was in a meeting yesterday and somebody was pitching really hard on something to a group and they said yes, and he kept on pitching. And I said, "What's the matter with you? Take yes for an answer."
Yep, I said, okay, I'm in. Yeah.
Yeah.
Just actually up until probably 4 or 5 months ago, I was nervous about debt because but now that we have we know our cost, and now we've lined up, well, actually probably over the last 6 months now, we've lined up so many partners that are ready to buy.
Yeah.
We would take debt in a second.
Yeah.
But so to manufacture containers, so once we're operational in Oxnard, which should be 30 to 45 days. Let's say
post-funding.
Yeah. And then we're 60 days after that to have the containers, and then we're 90 days to have them certified. Because the containers are a very interesting thing. We actually currently have to buy these little metal things that go up in the corners of containers. I'll show you real quick.
So they can stack, right?
No, can you see that little metal thing up in the corner?
Yeah.
Okay, so that actually, if you were to look at that, it has a serial number on it. And so that's certified by companies so that they're strong enough, they're manufactured under very specific specifications.
Yeah.
So we have to go through that certification process so that we can use the composite for that. But so having said that, so that's 90 days. So let's say 180 days from funding, we're fulfilling orders for the containers.
Filling orders, even if they were 1,000.
Oh yeah, well we'll start probably at 100,000 feet, so 1,500 a month.
Yeah, got it.
And probably anywhere from, depending on the size, and it just may be that the first is this. I don't know if everybody's aware, but the NATO and the DoD is partnered with Canada to build the largest port in the world in Halifax, Nova Scotia. Because now that the Arctic is open, they're going to be changing the shipping channel so it doesn't go down through the Panama Canal. So now you can go right over Canada, and then they're building this massive port that they're allocating over the years about $250 billion for. The group that's responsible for the first boots on the ground for energy and supply management, like they called me this morning, like pretty much every third day, "Mark, are we good to go?" So they want to put the turbines in there, but importantly, the containers, they want to purchase thousands of them. So, and that's a really, really good client. So as soon as we can get certified, they're ready to go. So, yeah.
Do you have any thoughts on what could cause it not to be certified?
Oh, no. Actually, we already went through the process in our old facility. We did, actually, you have to drop it from like 18 inches. Okay. And then, it has to show these different things. We had this group in from South Korea, and we said, okay, let's go higher. We wound up dropping a 20-foot container from 4.5 feet. And like everybody was, 50 feet away, this thing's going to shatter. Not even a little, there were some scratches, but that was it. So, but just for the testing, we used the certified ones that you would just buy from the market for our metal in the corners, so we could, they could be used and nobody would get in trouble. So we've been using those until ours would be certified, our corners.
But it was your composite
for the whole container.
Yeah.
But the corners, we purchased those.
Yeah.
So we could get to use right away with those. Because they just weren't certified.
Yeah.
but no, they're much stronger than steel. They'll 100% be certified.
Yeah. Okay, we got to get moving, but let's take
Okay.
this last question. Are you pursuing all four of these different markets from day one, or you will pursue them in stages? Please explain your rollout strategy. Not
Great
to mention,
question.
yeah,
So
and plus, it's been a long time, right? It's not like day one.
Yeah, exactly. So the construction materials are already in market. And so that's already going in Australia. So we're just going to let that one pretty much form out. It's interesting in that we have a couple of groups. Noel, I don't really remember the group with Christian and Craig out of the UK. But so, for instance, this group wants to provide, like today, $50 million to build the wind turbines in the UK. They want to provide 300 jobs. This has been a 10-month process, and it's already been approved at the government level. So we have multiple partners in different areas that want to help us with manufacturing right now in different places. So we think that the wind turbine at scale will be done in the UK pretty quickly. We will be doing the 500,000 square feet in either Texas or Nevada. It'll be a combination of the turbines and the containers. The housing will be with a third-party group out of Arkansas. They want to do the manufacturing. We'll license it to them. And Oxnard, go-to-market units done, certification done, coinciding with the build-out of the 500,000 square foot facility. In that, we're doing the turbine and the containers at the same time. And then Australia is already going on construction materials, and then the UK on the $50 million facility there for turbines. So that's the initial strategy.
Is that enough money?
Yeah, because the group in the UK, this is very interesting money. It's basically there's a very small interest. I think it's like 3% interest over many years. And then there's a group. So you'll see there's a YouTube video of me presenting in Salamanca, Spain. Noel, myself were there. So we just have a LOI from them to build a facility just outside of Madrid. And they provide all of the funding in this JV for the manufacturing. So our capital needs as we go are not very intensive. And our manufacturing needs are not very intensive. Like the equipment is very inexpensive compared. Now, if you're going to build 500,000 square feet of manufacturing, you would think, wow, this is a lot of capital. But the majority of it is just our forms. And that's these pretty low-tech tables. And once we built the form, that's a kind of a CapEx cost. And so once the form is made, then it's just filling it every 48 hours. So yeah, so and then we have very significant orders that will place deposits on those, and our margins on these are pretty high. So we can also use that to scale.
Yeah. I was going to ask you about the margins, but I wasn't going to make you put it on a recording.
Yeah. That's why I said they're good. Yeah, they're very good.
Yeah.
And with the wind turbine, that's probably actually our lowest margin. It's still very good, but with the turbine, if you look at our model, we're actually participating, because the question that you asked of what's the cost for production per kW, it's so small that we want to participate on the back end. So we're also on the PPA, that we're getting an ongoing revenue piece of wherever the turbine is used.
Yeah, that makes a lot of sense.
Yeah.
This has been super helpful, Mark. Thank you.
I just see that. There's questions. I didn't see the end of it, but just this one.
Yeah, somebody's
Okay.
super interested. So, Lena,
Would you-
so we'll make sure you get all that.
Okay.
Yeah.
Lena at
Lena, thank you.
Innovation 44. Okay.
Yeah.
Hi, Lena. Okay.
So, yeah,
Well,
this is
Arthur and
really
everybody, thank
great.
you so much for your time.
Yeah.
And yeah, I appreciate everybody. And I hope everybody groks the potential of what we're doing.
Yeah, we'll make sure everybody gets in touch and make and vice versa, make sure that they can get in touch with you. And we're going to do this again. So I think we have another date. So we'll alert everybody to that too, so they can invite others that may want to learn more as well. So
Okay, so hopefully our first date went good and we can go to a second date.
I want to date you all. Yeah, yeah, I'm easy. Yeah.
All right. Well,
Yeah.
thank you,
Thanks, Adele.
everybody.
Thank you
Have a
very
wonderful
much.
rest of the day.
Yeah.
Thank
As I
you.
would say, thank you for spending with us. The only thing you can't make more of, the
Fine,
Family
yep.
Office Insights community, your time. Thank you again. Till next time. Thanks.
Many blessings.
Thank you. Take care.